In progress.
Today, we're embarking on a deep dive into one of the most exciting intersections of modern technology and medicine, using advanced artificial intelligence to fight cancer. Specifically, we'll be unpacking our recent systematic review and novel methodological framework published in an IEEE-style paper, titled Graph-Based Deep Learning for Multi-Omics Integration in Head and Neck Cancer. My name is Isurulayan Awajig, and alongside my colleague Himashika Weezinghe, we've been working to address a critical challenge in precision oncology. If you're interested in AI, machine learning, healthcare, or you're simply curious about how technology is revolutionizing medicine, you're in the right place. By the end of this video, you'll understand why head and neck cancer is such a complex puzzle for doctors and researchers, what multi-omics data is and why integrating it is so difficult, how graph neural networks provide a revolutionary solution, the details of our proposed model and its exceptional results, and most importantly, what this all means for the future of personalized cancer treatment. Let's get started. Our story begins with the disease itself, head and neck squamous cell carcinoma, or HNSCC. This isn't a single, uniform disease. It's an aggressive cancer that arises in the mucosal lining of places like the mouth, throat, and voice box. It's notoriously complex and heterogeneous, meaning no two patients' cancers are exactly alike. This heterogeneity is driven by diverse causes, primarily tobacco use, alcohol consumption, and infection with the human papillomavirus, or HPV. This last factor is crucial. HPV-positive and HPV-negative HNSCC are essentially two different molecular diseases with vastly different clinical outcomes. HPV-positive patients often respond much better to treatment. This variability is why the old one-size-fits-all approach to cancer treatment is failing. We need precision oncology. Precision oncology aims to tailor medical treatment to the individual characteristics of each patient and their specific tumor. And how do we understand these characteristics? Through data. A lot of it. We now have the technology to sequence a tumor's genome, its DNA blueprint, its transcriptome, the RNA messages being sent, its epigenome, the chemical modifications controlling gene activity, and its proteome, the proteins actually doing the work. This collective data is called multi-omics data. The central hypothesis is that by integrating all these layers of information, we can unravel the complex molecular mechanisms driving a patient's cancer, predict how it will behave, and choose the best possible therapy. This sounds great in theory, but in practice, integrating multi-omics data is a monumental challenge. Why? Let's break down the main problems. The curse of dimensionality. Each omics dataset can have tens of thousands of features, example 20,000 genes, but only a few hundred patients. This is a statistical nightmare. It's like trying to find a single specific grain of sand on a beach with a blurry, oversized map. Data heterogeneity. Each omics type is fundamentally different. Gene expression values, DNA methylation percentages, and protein abundances are on completely different scales and have different statistical properties. Concatenating them into one big spreadsheet doesn't capture their unique structures. Missing data. In the real world, it's extremely rare for a single patient to have a complete multi-omics profile. You might have genomic data for 500 patients, but only 300 have methylation data, and only 200 have proteomic data. Most standard AI models just break when data is missing. Nonlinear relationships. Biological systems are not linear. The relationship between a gene's mutation and a protein's level isn't a simple straight line. It's a complex, dynamic network of interactions. Traditional machine learning models like support vector machines, SVMs, or random forests often struggle to capture this complexity. The black box problem: even if a complex model like a deep neural network gets good predictions, it's often a black box. A doctor can't trust an AI that says this patient is high risk without understanding why. For clinical adoption, we need interpretability and biological insights, not just accuracy. So, we have this incredibly rich, multifaceted data source that holds the key to personalized medicine, but our traditional tools are too blunt to properly use it. We need a new paradigm. This new paradigm comes from a powerful branch of AI called graph-based deep learning. But first, what is a graph? In computer science, a graph is simply a collection of nodes, or vertices, connected by edges, or links. Think of it as a network. This is powerful because biology is inherently graphical. Your genes interact in pathways. Proteins form complexes. Cells communicate. A graph is the natural mathematical structure to represent this. Instead of forcing our biological data into a spreadsheet, we can model it as it truly is, a network. Graph neural networks, or GNNs, are a class of deep learning models designed specifically to learn from data structured as graphs. Their core operation is called message passing or neighborhood aggregation. Here's how it works: a node in the graph doesn't just look at its own features, it looks at the features of its neighbors. It aggregates that information to form a more informed representation of itself. This process happens across multiple layers, allowing each node to gather information from its immediate neighbors, then their neighbors, and so on. It's a powerful way to capture the relational context of each data point. There are different types of GNNs. Two key ones we use are Graph Convolutional Networks, GCNs. They perform a weighted aggregation from a node's neighbors. Graph Attention Networks, GATs. This is a more advanced version. Instead of treating all neighbors equally, a GAT learns which neighbors are more important and assigns higher weights to them. This adds a layer of dynamic adaptability and interpretability. This ability to model relationships makes GNNs the perfect architecture for integrating multi-omics data. Now, let's see how researchers are applying this. In our paper, we conducted a systematic review of the current state of the art. We found that graph-based multi-omics integration methods can be broadly categorized into two main philosophies, each with its own strengths. The first approach builds patient similarity networks, PSNs. Here, each node is a patient. We take one omics type, say gene expression, and we calculate how similar every patient is to every other patient based on their gene expression profile. We use metrics like cosine similarity. We then connect each patient to their k-nearest neighbors, their most similar counterparts. This gives us a graph for gene expression. We repeat this for DNA methylation, mRNA, etc., creating one graph per omics type. The second approach is fundamentally different. Here, each node is a biological entity, like a gene or a protein. The edges are not calculated from data, they are prior knowledge mined from massive biological databases like string for protein-protein interactions, or KIG for pathways. This graph is a fixed scaffold of known biology. We then project patient data onto this graph. For example, the initial feature of a gene node could be its expression level in a particular patient. A GNN then propagates information across this known biological network. A gene with a normal expression level might be deemed important because it's a hub connected to many other dysregulated genes. The updated gene embeddings are then pooled to create a patient representation. The huge advantage here is interpretability. Because the graph is made of real biological entities, we can trace the model's decision back to specific genes and pathways, giving us crucial biological insights. Of course, the best models are now hybrids. They might build both a patient similarity network and a biological knowledge graph, fusing them together. Others use autoencoders first to reduce noise and dimensionality before building cleaner, more robust graphs. The field is rapidly evolving towards these sophisticated, multi-view architectures. So, these graph-based methods show immense promise on large, pan-cancer datasets like the Cancer Genome Atlas, or TCGA. But when we focus on our specific use case head and neck cancer, several critical research gaps become apparent, hindering clinical translation. Gap 1, the black box problem. While GATs help, many models are still not interpretable enough. An oncologist needs to know why a patient is stratified as high risk. Which genes? Which pathways? Without this, they won't trust the AI. Gap 2, data imbalance and missingness. This is a huge issue in HNSCC. HPV positive and HPV negative patients are not equally represented. If you have 400 HPV negative and 100 HPV positive patients, a naive model will become biased towards predicting HPV negative because it sees more examples. Furthermore, missing omics data is the norm, not the exception. We need models robust to these real-world issues. Gap 3, the translation gap. Many models are great academic exercises but aren't built for the clinic. They need to be integrated into hospital air systems, have user-friendly interfaces, and be validated on new, prospective data, not just retrospective benchmarks like TCGA. Gap 4, the need for HNSCC-specific models. Applying generic pan-cancer models risks washing out the unique molecular signature of HNSCC, especially its stark HPV divide. We need models designed explicitly for this cancer's reality. Our research wasn't just to review these gaps, but to propose a novel framework specifically designed to overcome them. This is the core of our paper, a novel, multi-view graph attention network framework designed for interpretability, robustness, and clinical actionability in HNSCC. Let's walk through the four main components, which you can see in this diagram. We start with a curated HNSCC dataset. We normalize each omics matrix and use a variational autoencoder, V, for dimensionality reduction to cut through noise and sparsity. Then, we build not one, but two distinct graphs to get multiple views of the problem. View 1, the biological knowledge graph, G_bio. Nodes are genes. Edges are taken from the string database, weighted by their interaction confidence scores. This graph is static and full of prior biological knowledge. View 2, the patient similarity graph, G_pat. Nodes are patients. Edges are drawn between a patient and their k-nearest neighbors based on the cosine similarity of their fused multi-omics profiles. This is the brain of our model. It's a two-layer hierarchical GAT that operates on both views. The first GAT layer operates on the biological graph, G_bio. It takes the initial gene features and uses message passing to learn new, context-aware gene embeddings. A gene's new representation is informed by all the proteins it interacts with. These sophisticated gene embeddings are then used to create enhanced patient representations. We aggregate the embeddings of the most altered genes in each patient. The second GAT layer operates on the patient graph, G_pat. It takes the initial patient data and the enhanced omics representations from the first layer. It then learns final patient embeddings by propagating information between similar patients. Crucially, the attention mechanism at both layers learns which gene interactions and which patient relationships are most important. To tackle the black box problem, we integrate GNN explainer. After the model makes a prediction, say, high risk, we run GNN explainer. It identifies a small, interpretable subgraph of the most crucial genes and patients that drove that decision. It provides a biological rationale, pointing to key pathways. This is a huge step towards building trust with clinicians. Finally, For robustness, we treat patients with missing omics data as unlabeled nodes in the patient graph. The graph structure itself allows information to propagate from patients with complete data, labeled nodes, to those with missing data. This imputes the missing values in a smart, task-specific way within the latent space, rather than relying on crude statistical imputation. To directly address the critical issue of class imbalance, we didn't just use the raw TCGA HNSCC data. We constructed a novel, rigorously curated, and balanced dataset. We started with all available HPV-positive cases. Then, we used a stratified sampling technique to select a random subset of HPV-negative cases that exactly matches the number of HPV-positive cases. Crucially, we stratified by clinical variables like tumor stage and gender to ensure our selected HPV-negative subset is truly representative and not biased. The result is a benchmark dataset with a perfect 1:1 ratio of HPV plus to HPV patients. We will be making this dataset publicly available on Zenodo and GitHub to promote fairness, reproducibility, and further research in the field. Now, for the moment of truth. How did our proposed framework perform? The results were, frankly, exceptional. Result 1. Prediction accuracy. For the critical task of predicting HPV status, a key prognostic factor, our model achieved a final test accuracy of 94.7% and a near-perfect AUC score of 0.9900. This significantly outperformed traditional machine learning baselines like SVMs and random forests, as well as other non-graph and graph-based deep learning models. The training was stable and robust, showing no signs of overfitting. Result 2, the patient network. The patient similarity network we built wasn't just a mathematical construct, it captured real biology. It consisted of 5,000 patients connected by 75,000 meaningful edges based on their multi-omics profiles. Result 3, interpretability. This is where it gets exciting. Using GNN explainer, we could see why the model made its predictions. For 5 representative patients, we generated these clear, visual charts showing the importance of genomic, transcriptomic, and epigenomic features. We moved from a black box to a glass box. Result 4, clinical validation, survival analysis. We stratified patients into low, medium, and high-risk groups based on our model's predictions. The resulting survival curves showed a clear, statistically significant separation, p0.001. The high-risk group had a drastically worse prognosis. This proves our model's predictions are clinically relevant. Furthermore, when we compared survival by actual versus predicted HPV status, the curves were nearly identical, validating our model's accuracy. Result 5, biomarker discovery. Finally, our model acted as a powerful discovery engine. We identified the top 20 most influential features for predicting HPV status. The list was dominated by gene expression features. The top 5 biomarkers GEXP_22, GEXP_17, GEXP_26, GEXP_13, and GEXP_12 all showed incredibly strong positive correlations with HPV-positive status. For example, GEXP_22 had a correlation coefficient of 0.8223. The distribution plot for this top biomarker shows a clear separation between HPV-positive and negative cohorts, visually confirming its power. These are now strong candidates for future wet lab validation and could lead to new therapeutic targets. So, what does all this mean? Let's conclude. We have demonstrated that graph-based deep learning is not just a trendy tool but a fundamental paradigm shift for multi-omics integration in oncology. By modeling biological data as the complex networks they truly are, GNNs like our proposed framework offer superior predictive power and, crucially, interpretable insights. Our work provides a clear roadmap to overcome the major hurdles blocking the clinical adoption of AI in cancer care, the black box problem, data issues, and the translation gap. We've shown it's possible to build models that are both highly accurate and biologically explainable. The future of precision oncology lies in this direction: interpretable, robust, and clinically actionable AI systems. Systems that don't just output a risk score but provide a biological narrative that a doctor can use to make a better decision. Systems that are built from the ground up to handle the messiness of real-world clinical data. This research is a significant step towards a future where every cancer patient receives a treatment plan as unique as their own tumor's molecular signature. It's an incredibly exciting field to be in. Thank you for taking the time to explore this deep and complex topic with me. If you found this explanation helpful, please give the video a thumbs up, and subscribe to the channel for more content on AI in healthcare. The full paper will be linked in the description below. If you have any questions or thoughts, please leave them in the comments. I'd love to hear from you and start a discussion. This is how we push science forward together. Until next time, thank you for watching.